Hi. Today I'm going to tell you 100 sleepy facts about dark matter, perfect if you want to relax a bit and learn something new about one of the greatest mysteries of the universe. Enjoy listening. 1. Dark matter makes up about 27% of the universe. Scientists discovered that ordinary matter, stars, planets, gas, and dust, accounts for only about 5% of everything that exists. The rest is hidden in dark matter and dark energy. This means that the universe we see with our eyes and telescopes is just a tiny fraction of reality. Without dark matter, galaxies would not hold together as they do. It acts like an invisible framework shaping the cosmos. 2. Dark matter cannot be seen directly. It does not emit, reflect, or absorb light, which means telescopes cannot capture it the way they capture stars. Instead, we only know it exists because of the effects it has on visible matter. This is why it's called dark. Its presence is revealed through gravity, not light. 3. Dark matter reveals itself through gravitational effects. When scientists studied the rotation of galaxies, they found that stars moved as if far more mass existed than what was visible. This extra mass is explained by dark matter, which provides the unseen gravitational pull. Without it, galaxies would fly apart. Dark matter acts as an invisible glue binding cosmic structures. 4. The concept of dark matter was first proposed in the 1930s. Swiss astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving too fast to be held together by visible matter alone. He suggested that some kind of missing mass must be present. At the time, his idea was controversial and largely ignored. Decades later, new evidence confirmed his prediction, and the mystery of dark matter became one of science's greatest puzzles. 5. Dark matter is not made of atoms like ordinary matter. Unlike stars, planets, or people, dark matter does not consist of protons, neutrons, and electrons. It must be something entirely different, made of unknown particles. Physicists propose candidates such as WIMPs, weakly interacting massive particles, or axions. These particles, if real, would explain why dark matter is invisible but still exerts gravity. 6. Dark matter helps galaxies form and stay together. In the early universe, gravity from dark matter pulled gas and dust into clumps, which later became galaxies. Without dark matter, the universe would be a scattered place with far fewer stars. Even today, dark matter halos surround galaxies, holding them intact. This invisible scaffolding shapes the large-scale structure of the cosmos. 7. The Milky Way is surrounded by a dark matter halo. Our galaxy is not just made of stars, planets, and nebulae, it also sits inside a massive, invisible bubble of dark matter. This halo extends far beyond the visible edges of the Milky Way. Without it, the galaxy's stars would drift away into space. In many ways, we are all living inside dark matter without even knowing it. 8. Dark matter outweighs ordinary matter by about 5 to 1. For every bit of matter we can see, there are about 5 times more hidden in dark matter. This means the universe is dominated by something we cannot directly observe. Despite this, we have mapped its presence through gravitational studies. It reminds us that reality is much bigger than what our eyes can detect. 9. Dark matter played a key role after the Big Bang. When the universe was still hot and dense, ordinary matter was spread out too evenly to clump together quickly. Dark matter, however, began forming gravitational wells that ordinary matter later fell into. This sped up the creation of galaxies and clusters. Without dark matter, the universe would look completely different today. 10. Dark matter does not interact with light. Unlike normal matter, dark matter neither shines nor blocks radiation. This makes it transparent to electromagnetic forces. Its invisibility is one of the main reasons it is so mysterious. Scientists must rely on indirect evidence to study it. 11. Dark matter is different from dark energy. Although the names sound similar, they describe two entirely separate mysteries. Dark matter provides extra gravity, while dark energy drives the accelerated expansion of the universe. Together, they dominate the universe, but in very different ways. If dark matter pulls things together, dark energy pushes them apart. 12. Some experiments aim to directly detect dark matter. Underground laboratories around the world are searching for the tiny signals dark matter particles might leave behind. These facilities use ultrasensitive detectors shielded from cosmic rays. So far, no clear detection has been made. But each experiment brings us closer to understanding what dark matter really is. 13. Gravitational lensing proves dark matter exists. When light from distant galaxies passes near clusters of matter, it bends due to gravity. Scientists found that the bending is far stronger than what visible matter alone can explain. This invisible mass is attributed to dark matter. It's like watching light curve around a hidden object in space. 14. Dark matter particles rarely interact with ordinary matter. If they exist, they can pass through us, the Earth, and even the Sun without being stopped. This makes them extremely difficult to study. Billions of dark matter particles may be streaming through your body right now without you noticing. Their ghost-like nature is both fascinating and frustrating for scientists. 15. Galaxy rotation curves are strong evidence for dark matter. Stars far from the center of galaxies orbit at almost the same speed as those closer in. According to the laws of gravity, outer stars should move more slowly, but they don't. This can only be explained if invisible matter is present, pulling everything with extra gravity. Dark matter provides the missing mass needed to make sense of these observations. 16. Dark matter may come in many forms. Some theories suggest it is made of exotic particles like WIMPs, axions, or sterile neutrinos. Others propose it could be made of entire objects like primordial black holes. Each possibility offers different clues about how the universe works. But so far, no one knows which, if any, is correct. 17. Dark matter could form structures we cannot see. If dark matter particles interact with each other, they might clump together into invisible objects or filaments. These structures could be shaping the universe in ways we don't yet understand. Some researchers even suggest there could be entire, dark galaxies, made almost entirely of dark matter. Such ideas expand the mystery even further. 18. Dark matter is everywhere, even around us. Although most of it is in space, dark matter particles likely pass through Earth constantly. They are part of the cosmic environment we live in. Yet because they rarely interact with normal matter, we don't notice them. We are literally swimming in an invisible ocean of dark matter. 19. Simulations of the universe require dark matter. When scientists model the cosmos on supercomputers, galaxies only form realistically if dark matter is included. Without it, the structures we see in the sky today would not exist. These simulations strongly support the idea that dark matter is real. They also help scientists predict where to look for its effects. 20. The search for dark matter is one of modern science's biggest challenges. Despite decades of effort, no one has directly detected a dark matter particle. Yet its gravitational fingerprints are undeniable. Understanding it could unlock answers to some of the deepest mysteries of physics and cosmology. The hunt for dark matter continues to push the limits of human knowledge. 21. Dark matter does not interact with light. It neither emits, absorbs, nor reflects electromagnetic radiation, making it invisible to telescopes. 22. Galaxies rotate too fast without dark matter. The observed speeds of stars in galaxies can only be explained if dark matter is providing additional gravity. 23. Dark matter is not dark energy. Dark matter has mass and creates gravitational pull, while dark energy drives the accelerated expansion of the universe. 24. Dark matter might make up galactic halos. Every galaxy, including our Milky Way, is thought to be surrounded by a large, spherical halo of dark matter. 25. The Bullet Cluster provides strong evidence. Observations of this colliding galaxy cluster show gravitational lensing that can't be explained by visible matter alone. 26. Dark matter is 5 times more common than visible matter. The universe contains about 5 times more dark matter than the combined mass of stars, planets, and gas. 27. Neutrinos are not dark matter. Although neutrinos are invisible and abundant, their tiny mass is too small to explain dark matter's gravitational effects. 28. Dark matter may consist of exotic particles. Candidates include WIMPs, weakly interacting massive particles, axions, and sterile neutrinos. 29. Dark matter clumps together. Unlike dark energy, dark matter forms structures, creating the cosmic scaffolding that galaxies are built upon. 30. Without dark matter, galaxies would fall apart. The visible matter alone isn't enough to hold galaxies together at their current speeds. 31. The first hints came from galaxy clusters. In the 1930s, Fritz Zwicky noticed that galaxies in clusters were moving too fast to be held by visible matter alone. 32. Gravitational lensing reveals dark matter. The bending of light by unseen mass provides one of the strongest tools for mapping dark matter. 33. Direct detection experiments are ongoing. Large underground detectors are built to try to catch rare interactions of dark matter particles with ordinary matter. 34. The Large Hadron Collider may produce dark matter. Physicists hope high-energy collisions could create dark matter particles that escape detectors, leaving missing energy signatures. 35. Simulations require dark matter. Computer models of galaxy and large-scale structure formation only work if dark matter is included. 36. Dark matter could be cold. The leading theory is cold dark matter, CDM, meaning the particles move slowly compared to the speed of light. 37. There are alternative theories. Some physicists propose modified Newtonian dynamics, as an alternative to dark matter, modifying gravity instead. 38. Dark matter doesn't clump like stars. It spreads smoothly and invisibly, never forming planets, stars, or black holes the way ordinary matter does. 39. Dark matter affects cosmic microwave background, CMB. Tiny fluctuations in the CMB give evidence for the amount and role of dark matter in the early universe. 40. It may interact only through gravity. If dark matter interacts via no other force, then gravity is the only way we can detect its presence. 41. Dark matter explains galaxy cluster binding. When scientists observe clusters of galaxies, they notice that the visible matter, stars, gas, and dust, doesn't provide enough gravity to hold the cluster together. Dark matter is the invisible glue that explains why clusters don't fly apart. 42. It influenced the formation of the first galaxies. In the early universe, tiny fluctuations in dark matter density acted as seeds. Ordinary matter fell into these gravitational wells, leading to the first stars and galaxies. Without dark matter, galaxies might never have formed. 43. Dark matter halos extend far beyond galaxies. Although most visible stars and gas in a galaxy are concentrated in a disk or bulge, dark matter forms a much larger halo, stretching far beyond the visible edges. This halo can contain most of the galaxy's total mass. 44. Dark matter helps explain flat galaxy rotation curves. When astronomers measure the speed of stars at different distances from the galactic center, the speed remains nearly constant instead of decreasing. This flat curve is one of the strongest indicators of dark matter's presence. 45. Some dwarf galaxies are dominated by dark matter. Dwarf galaxies, which are small and faint, often contain very little visible matter compared to the amount of dark matter inferred. In some cases, they may be over 90% dark matter. 46. Dark matter may not be completely uniform. Although it is invisible, simulations suggest that dark matter forms filaments, clumps, and streams that thread through the universe, shaping the cosmic web of galaxies. 47. We live inside the Milky Way's dark matter halo. Right now, Earth is moving through a sea of dark matter particles. If WIMPs or other candidates exist, they may be passing through our planet constantly, undetected. 48. Seasonal variations could reveal dark matter. Some experiments suggest that Earth's movement around the Sun might cause a seasonal change in the number of dark matter particles detected, but results remain controversial. 49. Dark matter might explain galaxy collisions. When galaxies collide, their stars often pass through one another without many direct interactions. But dark matter influences the shape, timing, and dynamics of such collisions, making it an important factor in cosmic evolution. 50. It is not the same as black holes. Black holes are compact, visible through their gravitational effects on nearby stars and light. Dark matter, on the other hand, is diffuse, invisible, and spread across galaxies. 51. Primordial black holes were once considered dark matter. Some scientists suggested that black holes formed in the early universe could make up dark matter, but recent evidence rules out most scenarios where they are the dominant source. 52. Dark matter may leave footprints in star motion. By studying the precise movement of stars in our galaxy, especially using data from the Gaia spacecraft, astronomers hope to detect subtle signatures of dark matter's gravitational pull. 53. Dark matter might be detected indirectly. If dark matter particles collide and annihilate each other, they could release gamma rays or other signals. Telescopes like Fermi look for such indirect evidence in space. 54. Dark matter could have self-interactions. Most models assume it interacts only through gravity, but some theories suggest dark matter particles might interact weakly with each other, changing how galaxies evolve. 55. There might be a dark sector. Some scientists speculate that dark matter is just one part of an entire dark world of particles and forces, similar to ordinary matter but hidden from us except through gravity. 56. Dark matter affects galaxy shapes. Elliptical, spiral, and irregular galaxies all owe their stability and distribution of mass to dark matter halos. Without it, their structures wouldn't make sense with known physics. 57. Galaxy collisions separate dark matter and gas. In clusters like the Bullet cluster, gas clouds collide and slow down, but dark matter, detected through lensing, passes straight through. This separation shows dark matter is not made of ordinary atoms. 58. Dark matter's identity remains unknown. Despite decades of study, no experiment has conclusively detected a dark matter particle. Its exact nature remains one of the greatest unsolved mysteries in physics. 59. It may influence future technology. If scientists ever discover what dark matter really is, it could revolutionize our understanding of physics, and maybe even lead to new technologies, as quantum mechanics and relativity once did. 60. Dark matter research bridges multiple fields. Astrophysicists, particle physicists, and cosmologists all work together on dark matter studies, since solving the mystery requires both understanding the universe on the largest scales and probing the smallest particles. 61. Dark matter holds galaxy clusters together. When astronomers calculate the total visible matter in galaxy clusters, it falls far short of the mass required to keep them bound by gravity. Dark matter provides the missing mass that explains their stability. Without it, clusters would disperse over billions of years, but instead, they remain tightly connected. 62. It forms part of the cosmic scaffolding. Computer simulations show that dark matter formed filaments after the Big Bang, creating a vast cosmic web. Galaxies later formed along these filaments, showing that dark matter shaped the large-scale structure of the universe. This makes dark matter fundamental to the very architecture of the cosmos. 63. Dark matter halos are mostly spherical. While galaxies themselves often appear flat and disk-like, their surrounding dark matter halos are more spherical or ellipsoidal. These halos extend far beyond the visible stars, influencing how galaxies rotate and interact with one another. 64. Some galaxies may have almost no dark matter. Although most galaxies are dominated by dark matter, astronomers have found rare cases of galaxies that seem to contain little or none. These findings challenge existing theories and suggest dark matter may not distribute uniformly. 65. Dark matter might come in streams. As galaxies collide and merge, streams of dark matter may form, passing through space like invisible rivers. Earth could be traveling through such a stream, which might slightly enhance chances of detecting particles. 66. It affects gravitational lensing. Dark matter bends light from distant galaxies, creating arcs and distortions in telescope images. These effects allow astronomers to map dark matter distribution, even if they can't see it directly. This is one of the strongest proofs of its existence. 67. The Bullet cluster is strong evidence for dark matter. In this famous collision of galaxy clusters, visible matter, gas, separated from the unseen gravitational mass. This showed clearly that most mass wasn't in ordinary matter but in something invisible, dark matter. 68. Dark matter density changes across the universe. Some regions of space have higher concentrations of dark matter, creating gravitational hotspots. These regions attract ordinary matter, shaping where stars and galaxies form. 69. Dark matter moves slower than light. Unlike photons, which travel at light speed, dark matter is thought to be cold, meaning it moves relatively slowly compared to light. This slowness helps it clump together and form large structures. 70. There may also be warm, dark matter. Some theories propose particles that are not as slow as cold dark matter, but not as fast as neutrinos. Warm dark matter could explain certain galaxy formations that cold models struggle with. 71. Dark matter could interact via unknown forces. Physicists speculate it might have its own types of interactions, possibly a dark electromagnetism or even a dark photon. These forces would be invisible to us but shape dark matter behavior. 72. Dark matter is likely stable. For it to still exist since the Big Bang, dark matter must be made of particles that don't decay quickly. This stability makes it unique compared to unstable subatomic particles that vanish rapidly. 73. It may help explain galaxy rotation anomalies. In galaxies, outer stars rotate too fast for visible matter alone to account for. Dark matter provides the missing gravity that explains these fast, flat rotation curves. 74. Dark matter and dark energy are different. Although both are dark, they aren't the same. Dark matter pulls things together through gravity, while dark energy pushes the universe apart, driving cosmic expansion. 75. Some theories replace dark matter with modified gravity. Alternative theories like modified Newtonian dynamics, suggest changing the laws of gravity instead of invoking dark matter. But most evidence still strongly favors dark matter. 76. Dark matter may clump into subhalos. Even within galactic halos, dark matter might form smaller substructures. These subhalos could host dwarf galaxies or remain invisible, influencing nearby stars. 77. The universe could not look the same without dark matter. If dark matter didn't exist, galaxies might never have formed in time for life to appear. The cosmic web, stars, and even planetary systems may owe their existence to this mysterious component. 78. Some detectors are buried deep underground. To avoid cosmic rays and noise, dark matter detectors are placed in deep mines or under mountains. This shielding increases the chance of catching extremely rare particle interactions. 79. Cryogenic detectors may hold the key. Some experiments use ultracold crystals that could vibrate if struck by dark matter particles. Detecting these tiny vibrations may provide the first direct evidence of dark matter. 80. Dark matter inspires science fiction. Because of its mystery, dark matter often appears in novels, films, and video games. Writers imagine it as fuel for advanced civilizations or as a hidden power waiting to be harnessed. 81. Dark matter shapes galaxy collisions. When two galaxies crash into each other, their stars rarely collide directly because of the vast distances between them. However, their dark matter halos interact gravitationally, steering the overall motion of the galaxies. This invisible influence determines whether galaxies merge, separate, or form new structures. 82. Dark matter may affect black hole growth. Some theories suggest that supermassive black holes at galaxy centers grew faster because dark matter concentrated around them. By drawing in ordinary gas, these dark reservoirs may have fueled rapid black hole formation in the early universe. 83. Dark matter could be asymmetric. Ordinary matter has more particles than antimatter, which explains why we exist. Some scientists suggest dark matter may also be asymmetric, with more particles than anti-dark matter, shaping its behavior over billions of years. 84. The cosmic microwave background reveals its effects. The CMB, the faint afterglow of the Big Bang, carries tiny fluctuations that match models including dark matter. Without dark matter in those equations, the observed patterns cannot be explained. This is strong, independent evidence of its existence. 85. Dark matter may form caustics. In simulations, dark matter sometimes forms sharp density spikes called caustics, where particle flows intersect. These invisible features could affect how stars and gas move inside galaxies. 86. Our solar system might not be affected much. Although the Milky Way is full of dark matter, the density around our solar system is low. Dark matter doesn't noticeably affect planetary orbits, which are dominated by the sun's gravity. 87. Some experiments search for dark photons. A dark photon would be a force-carrying particle like the photon of electromagnetism, but connected to the dark sector. Detecting one could reveal a whole new hidden universe of interactions. 88. Dark matter streams might influence Earth. If our planet passes through a dense stream of dark matter, it could slightly increase the detection rate in underground laboratories. Seasonal or directional changes in signals might hint at such streams. 89. Dark matter could form exotic stars. Theories suggest that in the early universe, clouds of dark matter could have collapsed into stars powered not by fusion, but by dark matter annihilation. These dark stars would glow faintly in infrared light. 90. Dark matter research uses space telescopes. Satellites like Fermi and Euclid observe gamma rays, cosmic structures, and gravitational lensing. These space-based tools complement underground detectors by searching for indirect signals across the universe. 91. The Large Hadron Collider looks for dark matter. At CERN, proton collisions might create dark matter particles that escape detectors unseen. Scientists look for missing energy and momentum as indirect signs of new invisible particles. 92. Axions could also solve other puzzles. If axions exist as dark matter candidates, they could also explain why the strong nuclear force doesn't violate symmetry in strange ways. This makes axions a two-in-one solution to physics mysteries. 93. Dark matter distribution may affect timekeeping. Atomic clocks are so precise that passing dark matter clumps might slightly change their tick rates. Experiments are using networks of synchronized clocks to look for these tiny disturbances. 94. The universe's fate may depend on dark matter. If dark matter influences cosmic expansion more than expected, it could change predictions for the universe's ultimate fate. Whether the cosmos expands forever or slows down might partly depend on its properties. 95. Some galaxies appear made almost entirely of dark matter. A few ultra-diffuse galaxies show little visible mass but enormous gravitational pull. These strange galaxies are thought to be almost pure dark matter with a sprinkling of stars. 96. Dark matter may explain cosmic structure, missing satellites. Simulations predict more small galaxies around the Milky Way than we observe. Some suggest dark matter subhalos exist but don't have enough ordinary matter to shine, explaining the mismatch. 97. Gravitational waves might carry dark matter clues. As massive black holes merge, their gravitational wave signals could be slightly altered if dark matter halos surround them. Future detectors may be able to pick up these effects. 98. The search for dark matter unites global science. From underground labs in Italy and Canada to space telescopes orbiting Earth, researchers worldwide collaborate to uncover its nature. It is one of the most international scientific quests of our time. 99. Understanding dark matter could unlock new physics. Like how quantum mechanics and relativity reshaped science, discovering dark matter's true nature could revolutionize physics. It might even reveal hidden dimensions or unknown forces. 100. Dark matter reminds us how much we don't know. Even after centuries of studying the cosmos, most of its mass remains invisible and mysterious. Dark matter challenges our assumptions, showing that the universe is far stranger than human intuition suggests. Solving its mystery could redefine our place in the cosmos.